So yeah, recording is on. So welcome to this session about topology. Now, since there was some discussion earlier about this, I decided to have a couple of slides motivating actually why we care about topology, especially in machine learning. So I figured one way to actually motivate topology is actually discuss how it was developed, and it sort of boils down at least one first so the way we got to topology was from analysis. So like around about the 17th century, you had Newton and Leibniz that developed calculus independently. Um, that sparked quite a lot of interesting mathematics and science. But there was one problem that actually bothered mathematicians at that time, was that it was not very rigorously defined. At least there were not there were no rigorous foundations of some of the things manipulated, like compute derivatives. For example, infinitesimals, that was really something that people were bothered about, and like you had philosophers uh, flipping their shit. Actually, I think your mic is still open. Okay. So yeah, there were a lot of questions about, okay, is this whole calculus thing actually well defined? And it only took until the next century that and for the rigorous foundation to be provided by people like Bolzano, Cauchy, and Weierstrass, which introduced the famous or infamous epsilon delta formulation that sort of replaced these infinitesimals. So that was one first step. And so from this, I think that's maybe the lesson you could take out, is that topology in large part is about taming infinity. So specifically taming like infinity small or infinity large, or what happens if I have an infinite sequence and I want to talk about what happens at the end. So a large part of topology is about providing rigorous definitions of these notions of infinity and what happens when you take a limit, what's the proper definition of something continuous. But that's actually not all there is to topology, and quite often when like people learn about topology in the popular science context, they hear about in topology you cannot make the difference between a torus and a donut, and that's more the other part of topology, which you can trace it to stuff like graph theory, like so Euler's polyhedron formula, that if you take a polyhedron and take the number of edges, the number of faces, and the number of vertices, and I think it's the number of vertices minus the number of edges plus the number of faces, which should always be equal to 2 for a convex polyhedron. Stuff like the Harry-Ball theorem that says that if you have a vector field, a continuous vector field on a ball, there has to be a point where there's the vector field is 0, for example. And later other things that like homotopy and homology that were introduced by Poincaré. And that's, yeah, I think also maybe more 19th century roundabout. So that this other part of topologies, you could think of it as geometry without numbers, in the sense that there are many geometrical problems or geometrical situations where the actual details about the lengths or the angles of your problem don't really matter. It's only like global characteristics that matter, and so it's sort of an abstraction of some parts of your problem, and that turned out to be quite a powerful idea and has a lot of ramifications. But we'll probably more talking about the first part today. So the second part, okay, why should you actually care about topology for machine learning? Well, one reason you should care is that it gives you a principled way to talk about conversions for a bunch of different objects that aren't just real numbers. So if you want to talk about a sequence of functions, a sequence of sets, of graphs, or even computer programs, or even metric spaces, and you want to say, okay, does this sequence have a proper limit? The natural construction and principal construction to talk about this is by defining a topology. And it's especially important in machine learning for sequences functions, because when one of the central theorems of machine learning is the universal approximation theorem that tells you that you can approximate any continuous function with a neural network. There are some caveats, but that's essentially the essential content of the statement. And those are topological statements. It's saying, okay, any function of this class I can approximate like as precisely as I wish using these neural networks. And it also gives you some insights, and that's actually the other part of topology that gives you insights about neural networks. For example, there's a really great blog post by Chris Olah called Neural Networks, Manifolds, and Topology that does give some motivation of why, for example, you might want to have the hidden width, the hidden layer width, to be larger than the width of your input sources, or you might want to have a minimum amount of width to networks based on a topological argument. And another place where this comes up is whenever you have embeddings, for example, text embeddings or embeddings of any data sets. It's a very popular assumption is the manifold hypothesis that says, okay, my data is living on some low-dimensional manifold, usually differential, but does not always need to be. And manifold theory, a lot of it does boil down to topological characteristic. For example, how many different connected pieces does my manifold have, for example, or clusters in the machine learning context. So yeah, before we go on properly, so topology is one of those topics that goes quite deep in terms of abstraction. We won't be going very deep because one, we don't have time, and two, one should be careful of keeping oneself sane. So yeah, we'll mostly be staying on the upper part, maybe going deeper for the second session, but yeah, we won't go all the way down. So, yeah, the right is an example of like how much abstraction you can get with it. Okay, topology started out as studying like stuff like the real numbers, but real numbers have a lot of structure and it sort of hides a lot of details. And when people try to sort of define topology like that didn't depend on real numbers, you find that quite a lot of things start to break off, to shard in different directions. And that's why you have like stuff like these very fine distinction between very, very subtle notions. So yeah, anyway, so on with the actual content. So note that I'm going basically through most of the what I thought to be important in the reading, but like don't hesitate to interrupt me to ask questions at any time because there's actually quite a lot of content. So the central object in topology or in general topology is a topological space, which is simply a set X combined with some object tau, which is simply a collection of subsets of X. And it has to so this collection of subsets of X has to satisfy a couple of actions. So one is that the empty set and X have to be in my topology. So tau usually is the topology, and the pair X tau is the topological space. So the empty set and X have to be in my topology. Whenever I have two sets in my topology, usually also, by the way, we call these sets in the topology the open sets. So we have two open sets in my topology. I can take the intersection of these sets and it should still be in my topology. And so that's, by extension, this means that we can take finite intersections of open sets and still get an open set. And if I have an arbitrary collection of open sets, so arbitrary means it could be any cardinality. If I have this arbitrary collection of open sets, taking the union of those is also an open set. So those are very simple axioms. And we'll see as this develops that these are really all we need, or most of what we need to do stuff. Now, sort of when we say open set, it also suggests that maybe there's such a thing as a closed set. And indeed, a closed set or a subset F we'll say it's closed if its complement relative to X is an open set in the topology. And this actually gets us another characterization. So topologies are defined by the collection of open sets, but we could equally define them or characterize them by the closed set. So by definition, because the complement of the empty set is X and the complement of X is the empty set, these two are closed sets. And then if F and G are closed, then the union of F and G are closed. Note that we take the union because we're taking complements, and so finite unions of closed sets are closed, and arbitrary intersections of closed sets are closed. Note, however, that a set can be both open and closed at the same time. For example, the empty set and the whole set are both, and we call such a thing a clopen set, or neither. So we can also have a set that is neither open, neither closed. That depends on your topology. Okay, so let's give some examples. So there are two sort of straightforward examples one might try. So the first one is discrete topology. So let's take all my subsets and call them open. Very straightforward. The other one is the trivial topology. Let's say, okay, I just test only the empty set and X because I have to have them. But other than that, there are no other open sets. So, okay, those are sort of maybe not super interesting. The more classical one on the real numbers, for example, is the topology where my open sets are union of open intervals, and open intervals are noted this way. Okay, note that. So I think this is the sort of usual notation in English for open sets. There might be some confusion in my slides because what I was taught uh, that open intervals would be this way, which makes more sense to me. But yeah, be aware that if you see a set that looks like this is because I'm writing what I'm used to know, and I forgot that I'm addressing English people or English-speaking people. Okay, so that's the usual topology, and it's really the sort of what people are most used to and what comes up most often in machine learning. An interesting topology for other reason is called the serpentine place. So I take X to be the set 0, 1, so only two elements. And my topology is for open set I have the empty set because I have to, the singleton one, and then 0, 1, so X. And so the serpentine space is sort of the simplest non-trivial topological space because it's not a discrete topology because I don't have the singleton one. And actually, this topology has some applications in computer science actually, because there's actually a nice way to apply topology to computer science to define like stuff relating to recursive functions. But we can talk about that maybe later. So if you want to word, this is the keyword is denotational semantics for that. Okay, now an intuition I like to have or to say to people about topology, that a topology is like the set of pictures that you can make or draw on a canvas with a given set of brushes. So for example, the trivial topology, if it's the topology you get if your only tool is the fill tool, right? I can only fill the whole space or just have nothing at all. The discrete topology is the opposite. I can have an infinite thin, so I can take any point. It's like I have an infinitely thin point brush that lets me pick any point in my space, and that's my discrete topology. And then stuff like the Euclidean topology, that would be more brushes with non-zero thickness. So I can get I can draw pictures with like oops, like this, but I cannot have a brush with width 0. There has to be some non-zero width. And surprisingly, this gives a different topology than just the discrete topology. Okay, so I just mentioned the Euclidean topology, so we can sort of generalize this to like just arbitrary dimensions of n. So we define the open ball in Rn around some point x and some radius epsilon as simply the set of points that are within distance at most epsilon of x. And we define our Euclidean topology on Rn as simply the arbitrary unions of these open balls. And so you can sort of imagine sort of building this set as a picture of just having brushstroke with different radii and constructing an open set that way. And this is the first thing we already generalized. So the Euclidean topology is just one instance of what's called a metric topology, where simply whenever you have a metric space, so a set X with some distance function, so a metric that simply has to satisfy a couple of axioms. So it's a function that takes two elements of my space and gives me the distance. So first of all, the distance should be greater than 0, but the distance from a point to itself is always 0. And if I have 2 points that are such that their distance is 0, they're the same point. Obviously, the order of my points does not matter when I evaluate my function, and it should also satisfy the triangle inequality. And so, nice thing is that whenever I have a metric space, I can define a topology called the metric topology, and it by again constructing my open balls and just defining my topology to be arbitrary unions of these open balls. Now, okay, we say now that a topological space x tau is metrizable if I can find a metric that generates my topology. But importantly, there could be multiple metrics that generate my topology. So for example, on just the finite dimensional real vector spaces, my P norm, so defined as this way, but if you want an image of the open balls, you have some example down there, or the sort of LP norms. In finite dimensions, they all generate the same topology. But importantly, this is not the case in infinite dimensions. That's in infinite dimensions, we're actually jumping into functional analysis. Anyway, so a quick little one, but it's not super interesting. So the finite complement topology is a topology where any open set or any closed set outside of the X and the empty set has to be finite. That's one way you could do. But more interesting is the order topology. So maybe you don't have a metric space, but you may have an order on your space. So an ordered set is a set where I have an order relation that suggests, okay, X is smaller than X, X smaller than Y, and Y smaller than X implies X is equal to Y, and then I have that this smaller than relation is transitive. And again, I can define just a generic order topology on this set simply taking the arbitrary unit of one-sided intervals defined this way. And so that's again another topology I can define. And note that on the real numbers, this actually is the same as the Euclidean topology. But again, this breaks down if you have something else, maybe. And note that, for example, for the just n-dimensional real vector space, you do not have like just an order relation, so this does not work. Okay, so this is one example in the reading which I really liked, so I wanted to give it again. So it's sort of an example of a problem where you want to do something and you sort of build a topology that lets you do it. So here is a proof, a topological proof that there are infinitely many primes. And the way to do that is, okay, by taking for a and b in my integers, p being different than 0, we'll define our set NAB to be basically the set of affine sequences. So I have set of numbers of form a plus bn for with n in my integer. And so really it's basically I pick a point and I jump b by a b amount every time. And we'll generate a topology based on these sets. So we're just taking union of such sets. We will also declare we'll declare U and Z to be open if it's a union of these sets. Now, first of all, we actually have to show that this is in fact a topology. So, first of all, it's okay. No, this is wrong. Oh yeah, no, this is true. So, first of all, notice that I can take if I assume that I can take finite intersections, then obviously the empty set, I can just take like the even numbers and the odd numbers, take the intersection, that's the empty set. So the empty set is indeed open. And the whole space, well, I can just take, start from 0 and go by 1. So I get that the entire space is also an open set. And then the last axiom is a bit more tricky. So I know that I can take unions, that's not a problem. I just need to show that intersections of my open sets are open. And so, okay, let's take two open sets. And suppose that I have some A in their intersection. So because A is intersection, that means I can find a B1 such that there is a set NA B1 in my first open set. And I can find similarly a B2, so a step size B2 in my second open set, so that NA B2 is in my second open set. So that means that NA B1 times B2, I just take the product of both steps, that has to be in the intersection. And so I have found a set that, an open set that is in my intersection. So indeed it works. So nicely the thing is that actually these sets are also closed, because I can write NAB as just my Z set, so set difference with this union. So this boils down to just a finite intersection, and so it also works. So these open sets are also closed. So here it's interesting that every open set is also a closed set. Now, this is actually the end, or we can actually go to the end of the proof. So since any integer C different from -1 or 1 has at least one prime divisor P, that means that C will belong to this N0P, which means that this set Z minus 1 and 1 is simply the union of these NOPs, 0Ps for every prime number. And now suppose that there were only finitely many primes in Z, then this set here would be a closed set, right? Because it's a finite union of open sets. Hence, -1, 1 would be an open set. But this is a contradiction because this is a finite, so, right? This cannot be expressed as one of these NAB sets. And so, since it's a contradiction, there has to be infinitely many prime numbers. So, moral of the story, depending on your problem, choosing the topology is a good idea. This is maybe less the case for whenever you're doing approximation problem, but whenever you're studying stuff like in function analysis, it's very common to just tweak the topology you're using to suit your needs. Okay, so so let's move on to just continuity. So we know intuitively what a continuous function, and since we know how it works in the real numbers, it's fairly straightforward to just define what it means for metric spaces. So we have two metric spaces, x and y, and a function between them. I'll say that this function is continuous at some point x. If for any epsilon greater than 0, I can find some delta greater than 0, such that if the distance in x between x and x prime is smaller than delta, that implies that the distance in y between f of x and f of x prime is smaller than epsilon. So this is just the standard epsilon delta definition of continuity. And I can sort of start rewriting it in terms of open balls as saying that, okay, the image f of the open ball in x around x of radius delta is contained in the open ball in y around f of x with radius epsilon. And so there are a few steps, but the general notion of continuity between just on arbitrary topological spaces, that if I have a function between two topological spaces, I say that it's continuous if for any open set in my output topology, so in my y, the inverse image, which may not, so f need not be invertible, but it should be understood that, okay, the set of all points in X that get mapped to this open set, so this inverse image should be an open set in my X topology. Now you might be wondering, okay, why do I need to take the inverse image? Right? Why not take just the direct image? So let's imagine I'll define a function between two topologies to be an open map if the image of an open set is an open set in the output space. And shouldn't this be a better definition of what a continuous function is? And actually, no. And I can give you a counterexample, the real numbers. Why is that? So let's just take the real numbers with the usual topology and just take f of x equal x squared. So obviously this is a continuous function, but if I look at f applied to the open set minus 1, 1, the result of that is 0, 1, but close on the 0. So this is not actually an open set. So as a result, I have a continuous map which is not open. So I think maybe this will give you a bit of intuition why we do need to take this inverse image, because there could be, like, maybe this function folds around. So for example, because x squared is folds the negative numbers, it folds them on the positive numbers. That's sort of why we have to account to take this inverse image to properly properly capture what continuity means. Okay, so let's give some more
Do you
examples.
know who was, do you
Sorry, go
know
ahead.
who was first to introduce this notion of continuity? Because I think, I don't know, I guess this is like, I think sneakily one of the deeper insights of topology is that, like we all can kind of think of like what a continuous function on R looks like. You're just like, okay, it's something that I can draw with my pen without picking up the pen. Um, but then, I don't know, like realizing that actually it's about this notion of maps of open sets. I don't know. It's just very. I remember when I first learned it, it was very surprising, and I'm just curious because you talked about the history before. Like who first kind of realized this?
So yeah, I briefly checked the history, but I haven't read too much of it. Probably something like Weierstrass, but at least only in the real sense of like epsilon delta.
Mm-hmm.
I'm not entirely certain, okay, which person like defined it this way first. Probably around that time. I know, for example, like if you look at Fréchet's, so actually Fréchet's thesis, um, he does a lot of work on topology. And interestingly, he sort of defined compact sets first. Like compact set seems to be more of a primitive notion in Fréchet's thesis than open sets. But I'm not entirely certain who defined continuity that way first. Maybe I'll check.
Skyblaze is telling me that it was Hein. Um,
Huh.
I can Skyblaze speak up for themselves and maybe because I don't know about this, but if you can enlighten us, I would really appreciate it.
Is that in the sorry in the stream chat?
Mm. Oh, gotcha. But Bolzano got there first informally. Interesting. Yeah, I don't know. This is
Okay.
yeah. I guess in a weird way, this reminds me of first learning that when we talk about cardinalities, defining them in terms of bijections. Like when your kind of normal notion of size doesn't work anymore for infinite sets. You're like, well, what we really want to think about now, the concept that still is useful is bijection, and I think like kind of reduce, like going from well, like I have this conception of what continuity means, but I can't really make it rigorous. It's not really sure how to, how to like apply that. And then realizing that the concept that you actually want is this other thing. I don't know. It seems like a similar conceptual move to me, but honestly, even deeper and more surprising. Um,
Yeah,
but yeah.
definitely there are a few flavors to this. Even if you look at, I think, like measure theory and measurable functions, they're also defined that way. But I think that's partly on purpose because they wanted to be, oh, let's just take this, the open set to construct the Boyle sigma algebra, and magically continuous functions are measurable.
Hmm.
But yeah, definitely some very subtle
Yeah.
things. But yeah, I would expect people like Heine and Bolzano. I think Bolzano it was like a monk or something, or I think I remember Bolzano was a bit of an interesting character and a precursor in what he did.
I don't even think that I know much about Hein. I'm the only thing that's coming to mind is the Hein-Borel theorem, but I can't even. Okay, yeah. Um, who was Eduard Hein? German, of course he was German. Died 1881. Cool. Well, thank you both for enlightening us. Um, yeah.
Anyway, so let's move on. So some examples of continuous function, and this all of these are in for arbitrary vector space. So any constant function is always continuous. That is fairly easy because there's only one value that it takes. So any open set, like the image in any open set, if I have taken open set does not contain this constant, obviously the pre-image is just the empty set, and any subset that contains the constant value, well, the pre-image is just the whole set. So trivially, I have that is continuous. Similarly, the identity function is always continuous because it just map open sets to open sets. Now, these last three are actually very interesting because the second one, you might see, you might get some kind of category flavors. That's one thing I liked about the source, that they gave a few like categorically motivated properties. So if I have two continuous functions, f from x to y and g from y to z, and I compose them, I also get a continuous function. So continuous functions are closed under composition. That's nice. And then the second one, any function from a discrete topological space is continuous for somewhat similar reason as for why constant functions are always continuous. And for any, and similarly, any function to a trivial topological space will always be continuous because I have only two possible cases for taking an open set in my image. And obviously, any continuous function from just classical analysis will be continuous in this sense. Okay, so that's nice, but notice that we lost, by defining continuity this way, we lost we lost the notion of continuity at a given point. Right? Maybe we would like to work with functions that aren't continuous everywhere, but maybe some function that is continuous in some part of my space. And so to do that, we need to introduce a notion of a neighborhood. So neighborhood is actually a keyword that we'll find pretty much all over the place in general math, but machine learning papers. Like, okay, within a certain neighborhood around this point, I can do x and x. So let's take a topological space and some point in it, and I say that a subset n is a neighborhood of x if, first of all, it contains x, and more importantly, there is an open set that contains x that is also contained in my set n. So I have sort of a little diagram here. And so n could be any set, but as long as it contains an open set that contains x, it's a neighborhood. Now, something you might have gathered from like the previous example of topology is that okay, we define just these sets of like a topology is any like all the open sets, but typically we sort of have like a few open sets, a smaller collection of open sets that we use to construct the others. And similarly, we can ask about, we can do the same for neighborhoods. So we say that a collection of sets in X, subset of X, is a neighborhood basis of X if any item in that collection is a neighborhood of X, and any neighborhood of X contains an element of my basis. So for example, in the classical topology, taking my open balls around X of radius 1 over n, this gives me a neighborhood basis because you can imagine it's basically like mature schedules, right? I just have these concentric balls around my point. And so any neighborhood has to contain one of these because I can just go, can just take n small large enough that the small ball of radius 1 over n is contained in my neighborhood. So with neighborhoods, we can actually define what it means for a function to be continuous at a given point. So a function is continuous at point x if for any neighborhood n of f of x, so a neighborhood in y, I can find a neighborhood m of x in the x topology such that the image of m is contained in n. So sort of straightforward if you go from the original definition. And note that due to the way we define these neighborhood bases, it's actually to check that a function is continuous at point, we only need to check the condition on just my neighborhood basis. Because any neighborhood I can just sort of reduce to an element of my neighborhood basis, which means so f of x is continuous at x is for any neighborhood basis of f of x, I can find that these inverse image the inverse image of my neighborhood is a neighborhood basis for x. And so the last theorem to sort of bring things down, the global continuity is simply equivalent to local continuity at every point. That's because it's topology, it has to be checked. Okay, so we have continuous functions. What about continuous functions that are invertible? So if I just take a function that is invertible and continuous, it does not necessarily mean that the inverse of that function is continuous, but if it is the case, so I have a function that is bijective and both the function and its inverse and continuous, we'll call that a homeomorphism. And the homeomorphism, you can think of them as saying, okay, these two topological lists are equivalent, and we define that whenever I have an homeomorphism between two topological spaces, we'll say that these two spaces are homeomorphic, and this is in fact an equivalence relation. So equivalence relation not only in terms of the spaces, but in the open sets. So I map open sets to open sets between the two, and that means that if I have two homeomorphic spaces, I really cannot distinguish between them based on the topological structure. So that's what that means when people say that the donut is a topologist cannot distinguish between a donut and a coffee mug because he only knows the topology, and as far as the topology is concerned, these two are really equivalent. So he has no other information. Okay, so back when we defined a neighborhood basis, it would be nice if we could actually define sort of a basis but for the whole topology. And so we can actually do that. So, and this is also back to my example of like the paintbrushes. So we said that a collection of subsets, is a basis for my topology if my topology is just generated by taking arbitrary unions of the elements of my basis. So okay, I'm handling the arbitrary union part, but remember a topology is so defined by I can only take finite intersections. So for that, we define S to be a subbasis of my topology if I can generate, if I take B as all the finite intersections of the elements of my subbasis, this is a basis for my topological space. So in a sense, a subbasis is just all the paintbrushes I need for to generate my topology, both with intersections and unions. And the nice thing is that okay, for a topological space, I can try and find a subbasis for it, but really, I could take any set S and generate a topology with that set. And typically, we call that the topology generated by S. And so this is nice because really this S here, it's arbitrary. I could take whatever I want to generate my topology. So an example is that open balls on a on a metric space, I can take those on my subbasis and just generate the metric topology. So okay, I see a question: is the trivial intersection of the set with itself counted in that? I would assume so. So yeah, in the subbasis, obviously the elements of your subbasis, you can take just the intersection of one element. And I think, okay, depending on the source, you can say if I had taken an intersection with zero element, that's the empty set. So yeah, so sometimes there are conventions on what it means to take an intersection over an empty set. Okay, so I have another example based on this. So let's actually look at a topology generated by taking some kind of subbasis. So we'll define the half space in some Euclidean space as the set of points that satisfy this equation. So W transpose X plus B is greater than 0. For W, just a vector in Rn and B a real number. This might remind you of something. And so let's use these half planes. Note that these are open half planes in a sense because I'm taking strictly greater than, so the delineation is not included in my set. So let's construct a topology by taking these as a subbasis. And now I claim that actually this topology is equivalent to the usual topology on the Euclidean space. And the proof is fairly simple. First of all, note that these sets here, they're actually open in my usual topology. So because my subbasis is already open in my usual topology, that means that any open set in my half space topology will also be an open set in my usual topology. So I know that at least the th tau h is included in the usual topology. And then to go the other way around, it's okay. It's a bit strictly my argument is not entirely correct, but it's easy to come up with one that is. So let's say I can approximate, like my argument is that if I can construct the element of a subbasis of the Euclidean topology using my half-space topology, then that means that I can recover the whole topology. So here what I'm saying, okay, let's take the the ball of radius epsilon around some point x. So this is let's say it's a sphere or a circle in this case. And here I'm taking the closed ball, and I'm saying here the closed ball I can get by just taking the intersections of all these. So here I'm taking the spaces that are tangent to my sphere and with the contents inwards. And I'm taking the intersection of all of these half planes or half spaces that are tangent to my ball. And roughly speaking, if I take this over all my W, which has norm 1, and okay, do some computation, right? And if I take the intersection of all of these, I get my closed ball in the end. And so with some hand waving, but actually there's a simpler proof for this, I get that my usual topology is also part of my half space topology, and so that means they're both equal. technically another way would simply take, okay, I can just take like intersection of three half spaces and get the triangle and then rotate it. So this is an open set and I can just rotate this triangle by 360 degrees and at the end I get a perfect circle. So okay, then obviously like this may remind you of just what happens in a neural network, and really in a sense like this is kind of like the natural topology to talk about ReLU networks or ReLU networks. And so by the fact that these topologies are the topology generated by this is the same as the Euclidean topology, this sort of tells you that at least on some intuitive level that ReLU networks essentially can approximate any continuous functions in a fairly hand-wavy manner, but I think that's good enough. Okay, any other questions? Or at least I see not Louis writing something. Okay, never mind. Okay, so this slide will we go fairly quickly over it because this is a bit down in the iceberg. So we say that a topology is first countable if there is a countable neighborhood basis for any point x. So for example, in the metric topology, I can just take the Bowles of radius 1 over n, and then we'll say that set is second countable if the whole space has a countable basis. Now, why we might care about this, it won't become very clear here, because we pretty much always work where in contexts where at least we have a first countable space and you perhaps most often also a second countable. But these are sort of or some parts of the iceberg that go down. So for example, yeah, any metric space is first countable by the argument I showed previously, and Euclidean spaces they are also second countable because I can take my balls around the rational numbers, and because rational numbers are known to be dense in the real numbers, these are enough to just get everything. Okay, so I see Louis, not Lewis's comment. So you need three intersecting lines to enclose a circle. Yeah, okay. So yeah, basically what I showed here. So yeah. Okay, so aside from this moving down the iceberg, we're staying here into actual generally useful. So okay, we know we know about topological space, about continuous functions, but what are operations and stuff we can do to just make new topologies or topological spaces out of one we have. So a very simple one is, okay, let's say I have a topology, or more exactly a topological space, and I have a subset of my set X. I would like maybe to just only look in my subspace and get a topology on it, and this is called a subspace topology, and it's simply defined as taking the intersection between my subset A with all the open spaces in my topology, open sets in my topology. Notice that if any of these does not contain A, it's simply the empty set, and so I just get like many copies of the empty set out of this, but at the end I still get the empty set. So this is in fact a topology. Another definition is that given the inclusion function that simply goes from A to X, like it literally just map an element of A to where it is in X, the subspace topology is the smallest topology which makes this inclusion map continuous. Now the smallest here is it means the topology with the fewest open sets. Now, really, I mostly brought this example or this definition up because it's quite often it comes up that we define a topology by some functions or list of functions that we want to be continuous in that topology. So this is a thing that comes up quite often, that we want like we just have some function that we want to be continuous, and so we construct the smallest topology, so the simplest topology where these functions are continuous. Now, if I can take the subspace topology, I can actually do a few interesting things. So for example, if I have a topological space in some subset of my space, I can find the largest open set U, which is contained in A, and it's called the interior of A. So I can find the largest open set contained in A, and there's a few notations, sometimes int for interior, or int A, or A circle, and it's simply defined as the union of all the open sets that are contained in A. And note that because I'm taking a union of an arbitrary union of open sets, this is in fact still an open set. And similarly, there I can find a smallest closed set that contains A. It is called the closure of A, and it's defined as simply the intersection of all the closed sets that contain A. I go back to this diagram, and then I have a closed set. I can also talk about the boundary of A, which is simply the closure of A and intersected with the closure of the complement of A. And so this is in fact not an empty set. You can also define as simply the closure of A minus the interior of A. And it's clear with a picture. So, for example, suppose that this is my set A, and I have this sort of colored line denoting that okay, these elements on the border of my set are also in my set, and they have no it's like an open interval, right? I can get as close as I close, but then I cannot reach the boundary. And so then the interior would simply be just the set without this extra boundary here. The closure will be okay, the interior plus all the stuff on the boundary, and then the boundary is simply okay, just this line. So hopefully this makes things a bit clearer about like the difference between closed and open set, at least in the usual topology. Like you could construct arbitrary topologies to make things a bit more complicated, but that's roughly the intuition. Now, okay, if I have a subset that its closure, such that its closure is the whole space, we say that this subset is dense. For example, the set of rational numbers is famously dense in X because it's a countable set, but I can find, for any real number, I can find a rational number that gets arbitrarily close to it. And so in this way, that's an example of a set that is dense and in fact countable, but its closure is the whole space, which is uncountable. I think, another word for whenever you have a topological space that has a countable dense set, we say that it's a separable space. Okay, moving on, so we have boundaries and closures and so on. So one thing we can make with that is talk about limit points. So limit points or points of accumulation of some set A if X is in the closure of A minus the singleton X. So for example, this would be in this case, so any point on the interior, obviously I can just, it's in the closure. If it's on the boundary, it's also included in the closure, so no problem. If it is not a point of accumulation, we call that an isolated point, and I can define it, say, okay, I can find some neighborhood of X that does not contain A, or has no intersection with A, and this would be like on this drawing on the bottom, right? Maybe this point is still in my, so this is my whole set, but X here, like it's separated, it's isolated from the whole, and so it's it's an isolated point. So interesting property is that the closure of A is simply A plus all the limit points of A. So a closed set is a set that contains all its limit points. Now, again, this is sort of a global definition of limit point, and we'd like to sort of link it to limits of sequences. And so because we had defined continuous functions, it's actually very straightforward to define what it means for a sequence to converge. So we see that a sequence xn in my topological space X converges to some point X if for every neighborhood B of X I can find some integer m such that for any n greater than m, so yeah, for any n greater than m, the points of my sequence are in that neighborhood. And if you think about the classical notion of convergence, this is sort of the same idea, right? Because in the usual topology, my neighborhoods, I can characterize them as simply my open balls around X. And so this is the same idea, but here, because it could be an arbitrary topology, it is not necessarily the case that I have a unique sequence, right? Maybe, like for example, imagine that my topology is the trivial topology. Then there's only one neighborhood, the whole space. And so in the trivial topology, any sequence converges to every point. So do note that depending on your topology, you can have infinitely many, you can have more than one limit. But the Schwarzschild radius of an arbitrary set. Not sure what that's supposed to mean, but yeah, okay, no, I see what you mean. Yeah, I won't try to explain it, but yeah, it's a funny joke. Sorry. But okay, for example, if you have, I think we'll see in the probably the next time, but there are some properties that let you know that any a sequence has an only one limit if it converges, and that's one definition is Hausdorff. But for example, in metric spaces, because you have these neighborhoods that go arbitrarily fine around a point, in fact, any limit can only have ones up to, if it converges, the limit is unique. So metric spaces, unique limits. And there with me, we're almost to the end. So another nice thing we'd like to do is taking topological products. So right. So let's say I have two topological spaces x and y, and I'd like to define a topology on the Cartesian product x cross y. Now, importantly, this Cartesian product, it also comes with these projection maps, right? If I have something in x and y, I can take the first element and go to x, or the second element and go to y. And so we want to construct a topology on this, x and y, such that these projection maps are continuous. I told you that this was very common. This is another example. And so if they have to be continuous, that means if I have some open set in my X topology, its inverse image, which is very straightforward, only U cross Y, and exactly the same way for the V, for a V in an open set on Y. So these, I know, these are examples of sets I know that have to be in my topology. And okay, I can take the intersection of those, right? Because I assume that I can take finite intersections of my open sets. That means that U cross V also has to be an open set. And so this tells us that, okay, my product topology is just arbitrary unions of these open sets, Ui cross Vi for I in some sets. So assume that I have a way to just create a family of these open sets. Now, this is something I mentioned at the beginning, so we can also define the product topology for infinitely many topologies. So let's say I have a family of topological spaces indexed by I, and I can define the product topology by, again, taking these here infinite Cartesian products of open sets. But importantly, these open sets here, I can only have finitely many that are, sorry, almost all of them, so except for a finite number of them, they must all be my whole space xi. The reason for that, right, is that in this step we construct we constructed this by taking intersection, and we can only take finitely many intersections. So it's sort of why we can only have finitely many i's that are different from the xi. And this is mostly important whenever you stumble into functional analysis, for example, because a trivial example of these infinite product topologies would be just the set of sequences of real numbers, right? This is an infinite dimensional vector space, or you could say it's a product of like r times r to infinity, and so already see some weird stuff around infinity. Okay, another really nice categorical property, like in fact this is maybe one of the canonical example of what's called a universal property in category theory, is that the product topology is unique in a particular sense, which is that if I have any topological space Z that has continuous maps to x and y, I can always find a function f from Z. So note that all of these functions here are continuous, and I can always find a function f that goes from Z to the product Z and Y, such that these f of x, fx, and fy functions can just be expressed as taking the projection, so pi x composed with f and pi y composed with f. So what this tells, this is in category, this tells us that okay, maybe Z like claims to be also a product topology on for x and y, but really because it can factor it into these, really x cross y is the real product topology. Like any other topology can just be factored in terms of it, which it might not be the case. Like it might not go the other way around. Okay, side question: if the maps are discontinuous, does that directly or easily correspond to an increase in dimensionality of the resultant topology? Um, so I think that's maybe a bit difficult to answer because dimension itself is a topological notion. So I'm not entirely certain what your question means here. But maybe we can discuss that after I finish the slides. Okay, so the last one, and I only wanted to include it because actually it's useful. Yeah, think about it. So this last part, I'm including it because it's actually useful for other stuff we might talk about later on, and it's about gluing topologies. So whenever I have some topological space, and I can talk about taking an open cover, so just a set of open sets such that their union cover the entire space. Sorry. Um, yeah, so it covers, meaning that the union of all my UIs just cover the entire space, and so any open sets I can describe it in terms of this open cover. And similarly, any continuous function, I can sort of describe it in terms of its restriction on these UIs. So if I define fi to be simply f restricted to ui, so it's a continuous function from ui to y, taking the subspace topology. And in particular, the nice thing is that if I take fi and restrict it to the intersection between ui and uj, right? So maybe these open sets overlap, and usually they will. Because it came from the same function, taking fi and restricting it to the intersection should be the same as taking fj and restricting to the intersection, right? So they have to agree on their intersection. And conversely, if I have a set of fi that are defined on just my open sets, such that they also agree on their intersections, right? I could imagine gluing these different FIs to make a full function that is continuous. And so I can, in this sense, I'm gluing, like maybe I have different puzzle piece or like different maps of the same country. I can line them up to get a full map of the Earth or the country I'm looking at. So I can glue, like if I have an open cover of my topology base, can typically glue stuff that's defined on my open cover to get something that's defined on the whole space. And actually, I can also do that to construct a topological space. So if I have some set X, arbitrary, and I have a collection of subsets I, so xi, that whose union is X, and for each of these I have a topology. And specifically, it's a topology Ti on xi, such that for any I and j, the intersection of xi and j is also an open set in both of these topologies, and the induced topologies have to coincide. So if I have this, then I can again glue these topologies into a single topology on X, which will induce all of the TIs on each XA by the subspace topology. And okay, this might seem abstract, but this idea of gluing topologies is really important for defining manifolds and most importantly differential manifolds. So if you look, for example, at like an introduction to differential geometry, they'll talk about atlases of okay, you have maybe I cannot look at my whole space, but I can look at small pieces. And the important part, okay, if they share an intersection, they have to agree on the intersection, and that's where you can glue them. So this is one important thing that we can do with this gluing operation. And okay, this is even more abstract, but in stuff like sheaf theory and topos theory, if I'm not completely mistaken, because it's a bit abstract even for me, sheaf theory is basically what happens if you almost define your topology in terms of this gluing operation. But this is fairly abstract, so I don't think we'll get there anytime soon. So yeah, that was all I had for in terms of slides. So questions away.
I mean, if people do want to go there, there has been a couple of relatively recent graph neural network papers that directly kind of build on the idea of sheafs and like kind of basically putting an individual vector space at each individual node of your graph and then maps between the vector spaces where where there are edges. And I don't know that it works or particularly well, or like it does work, but it's kind of computationally very inefficient. Or just computationally hard. But it is, when people were asking about, motivation and like how does this apply to machine learning, like, you know, this idea of or these ideas of how do we make rigorous these potentially very subtle ideas of distance, of closeness, and close and far, same not the same. you know um, Topology is a really powerful tool for trying to encode the relationships that are in the data into a model. And so I don't know, it is something that we could try to talk about.
Yeah, I think you're right. I definitely see in the like category theory for AI. I think a lot of them use sheaves as like a main applied tool. But yeah, but because sheaves are a bit more abstract, I don't know. Maybe we'll cover it at some point. But okay, does maybe not Luis have managed to reframe his question, or does anyone else have questions or are confused about something?
Okay, so I have a very simple question, I guess. relating to one of the first slides. So you mentioned that uh, you could have an element that was neither in the open set or in the closed set or something.
Yeah,
Do you have an example?
actually I gave one.
Oh,
Yeah, so in the yeah, so for example, if you take just the real number of the usual topology and you take the set AB with the like inclusion on the bottom on A but B not included,
mm-hmm.
this set is neither open nor closed. And the way to see
Oh,
that
okay.
like because it's closed on the on one end but open on the other.
Yeah, yeah, right, right.
What are what are some non-trivial examples of clopen sets? Because like, so I know that like, the empty set is clopen, and then the whole space is clopen. Um, but what would be kind of like another example?
So I'm not super familiar with like the really non-trivial ones, but so the simple ones. Let's say I have a set that's composed. I build my topological space by just taking two space and they're not connected, right? So I have one space which is topology, and I just like add the other one. Then the connected components are also clopen sets, right?
Mm,
So this is a clopen set. This is a clopen set. In the prime number example, actually, right, there was this property that these NAB sets, which we defined as open, and it turns out they're also closed because I can write I can write it as the complement of a union of finitely many open sets, and so they're also so like this is an open set, and so the complement is closed. So these are this is another example of a non-trivial clopen set.
gotcha. Thank you.
Okay, does anyone else have questions, or maybe they'll ask them later? Because it's getting awfully warm in my room right now. So okay, I see not Louis still writing. Okay, now you're just trolling. Uh, anyway, so I think we can probably end it for today. So yeah, thanks everyone for coming. Hopefully this was instructive for everyone. And so next time I think it's Nev that should be presenting on the harmonic. Yeah, I think harmonic neural network. So this one will be much more applied because it will be actually a neural network paper about a neural network paper about like constructing. I think it's constructing neural networks that are invariant under harmonic operation. So it should be interesting.
All right. Yeah. Thank you. See you all next week.